Hi, welcome to this module on embedded metal corrosion. We will have 5 lectures in this, and the outline will be: first lecture we will cover what is the significance of corrosion and some fundamentals of corrosion, in which we will talk a little bit about the what happens in concrete also. And then lecture 2 we will cover in detail what is carbonation induced corrosion and chloride induced corrosion. Then 2 lectures on different type of steel reinforcement and what are the precautions to be taken when we use latest type of steel reinforcement which are available. And then lecture 5 we will cover corrosion exclusively, what is happening in pre-stress concrete system, both pre and post tension systems we will be covering. And now let us talk more about the significance of corrosion and fundamentals of corrosion. So, I am going to give you some examples of corrosion related failure or premature failure. That means, prematurely the steel started corroding before the design life or the target design life was achieved, the structure started corroding. So, this is one example, where on the picture on the left side you see that at the far end there is a ship, it actually hit the pillar and then the bridge collapsed, and what they did is, after that they reconstructed the bridge or another bridge right next to it, in which in about just 13 years you can see this pillar over here, in about 13 years it started severe corrosion, and then you can see that the severe corrosion of the post tension systems in the vertical tendons. And another example of premature corrosion, like or of corrosion, is Golden Gate Bridge. We spend a lot of money on this bridge to maintain the structure every year. There is a lot of corrosion related issues, and maintenance is a big job there. Another structure again in the developed world is the in Canada here, this is the Mercier bridge, also a couple of decades old bridge, but you can see that the bridge is severely corroding. The net which you see here is actually to protect it from falling down, and then you can see here there is a looks like ASR type of problem there. So, different type of deterioration mechanisms happen, deterioration happen in many of these structures, and what we are trying to tell here is it is leading to huge cost. And what is that cost? Is it is about 3 to 4% of GDP. Before getting into that, this pie chart which is showing the cost of corrosion, and this is made for USA, but more or less which will be similar to many other countries. So, I thought this will be a good example to show. What you see here is, if you look at the infrastructure, which is the green by here, you can see it is covering highway bridges, gas and liquid transmission pipelines, waterways, ports, railroads, etc., and utilities, which is this one, which covers about 35% of the cost of corrosion. That covers different hazardous material storage facilities, electrical utilities, telecommunication, gas distribution, drinking water, sewer systems. And what I want to focus here is, there are many many concrete elements are there in these two, and if you put them together, that utilities and transportation infrastructure, that is coming to be about 35 plus another 15 if you add, that is about 50% of the total cost of corrosion. So, we have a big job here to reduce this cost of corrosion associated with concrete structures. So, some statistics on this corrosion in the pie chart I showed earlier, I told that it was 3 to 4% of GDP. Now, if you look at in Indian case, we spend about 4 lakhs of crores, that is our rate or the cost of corrosion, annual cost of corrosion in 2014. As time passes, the cost is actually increasing, because we are constructing more and more structures, and also we are seeing premature corrosion in many of the structures much before it reaches its design life. Now, some other statistics I just want to mention here to emphasize that this is really a big problem. See, up to about 50% of the construction budgets actually is used for some kind of repair, and then 50% of the structures they experience a major repair within about 10 years, which is probably very short period. And now if you look at the amount of steel and cement which is produced, if you look at the steel, there is 30% of the steel is used for repair, and in case of cement 40% of the cement is used for repair. So, maybe these numbers look very large, but I have cross checked it with the same steel and cement industry. This is more or less correct. The steel that is actually used for replacing the existing steel, cement is also purchased for repair projects. So, this is really alarming, these two numbers. So, and this is what we have to really reduce, 3 to 4% GDP. We cannot keep on spending this much money in our future structures which we are building and the structures which we already have. So, we must have a corrosion protection strategy, that is essential to have a protection strategy. In other words, we should think of how to do a proper maintenance, and even in design life how to design the structure so that you will have minimum repair, and do a proper maintenance and repair. The repair itself should be durable. If the repair itself is not durable, then you will end up in doing many repairs, which will again increase the cost of corrosion. So, point is, now we have technology to actually achieve this corrosion free service life of 100 years and all that, but provided we do give more importance on quality of construction. Now, some of the structures, like why this is becoming, the corrosion cost is becoming more important today, is because we are constructing a lot of structures today, like these highway projects, seaports and then airports, and also when we talk about these major projects, there are also associated structures which are being built. For example, if you are constructing a road, there will be a lot of other structures which will come up all along the roads or on either side of the roads. So, that is also very important to have all these structures with quality in mind, otherwise we will face a huge repair and maintenance cost in the years to come. So, that is the main purpose of this course, is to make sure that we construct the current structures in good way with durability in mind, and at the same time we ensure that the way which we repair these structure or the existing structures are also going to be long lasting. Now, when we look at India as such, we have several the geographically different regions, and the climatic condition is different for different regions, and usually we think about corrosion. When we think about corrosion, we think about chloride induced corrosion. Probably one reason why we think like that is because we have a long coastline. You can see here this long coastline, and in this region here looks like a necklace, like I showed in the previous slide. This region, like if we have concrete structures along this region, those structures will be exposed to airborne chlorides, and at the same also the soil will be rich in chlorides in those structures. So, the foundation also may experience severe corrosion. So, we have to be very careful when we construct structures along the coastline. So, this is along the coastline, and also for carbonation is also, we usually think carbonation is not a major problem, but carbonation is also a major problem, because at about 60 to 70% humidity you can have very high carbonation also. But again, on the coastal zone we usually see that chloride is governing in most of the cases. However, we should also give enough importance for carbonation. And another thing is, if you are talking about any other structure in the interior or not on the coast, but away from the coast, we should also think about the local exposure condition, because let us say for example, you are building a chemical plant where a lot of salt is being used. So, that air next to the structure or the immediate to the concrete elements will have enough chlorides which will diffuse into the concrete element and can cause corrosion. So, even though in this map, for example, if the Delhi is coming to be moderate condition, or if some structure over here which is mild, and if I am actually constructing my chemical plant here, I may actually have very high chloride condition. So, we have to be really think about local environmental condition, not just the global conditions. This is very important to consider that. Now, let us look at what happens when iron, or how iron corrodes. So, I am going to show you this. See, how do we make steel? For example, we make steel from iron ore, and then we heat the iron ore in a blast furnace, and then you get the molten material. Then you mold it into a particular shape. Let us say if you are talking about a rebar, you mold it into a cylindrical shape. If you are talking about a structural steel, you may have I section or L angle section. So, whatever it is, you mold that into a particular shape and pass the steel through a die. So, here we get in this stage essentially, or essentially here we are actually giving more heat energy to the system, to the material, and here in this process we are giving or using more mechanical energy. So, essentially at this stage the material will have higher energy than the iron ore. Now, once you have this higher energy material, the tendency for that material to corrode will be more than when it converts to the iron ore. So, in short, steel will corrode at a faster rate than the iron ore. Now, than the iron, sorry. Now, once your steel is made, then you expose that steel to these different conditions. So, you, for example, if it is exposed to rainwater, you have moisture, then this indicates temperature, and then you also have chloride environment. If you are talking about the coastal line, you have chloride, and if you are talking about, luckily in India we do not use de-icing or anti-icing salts, but abroad if you go, you will see that especially in a cold climate region, you will see that during the winter you really are forced to actually pour this chloride solution or sprinkle chloride solution on the road, so that the ice flakes can be melted. And then, so when it is exposed, what happens is these chemical reactions, or the steel undergoes these chemical reactions, which goes from 1 to 3. So, eventually you get this Fe2O3, which has very similar structure like the iron ore. So, Nace defines this corrosion as extractive metallurgy in reverse direction. So, essentially from here to here, the rate at which it goes can be controlled. If you use stainless steel, I can reduce the rate of corrosion from steel to iron ore, or if I am using mild steel, it may be higher rate. So, that is only all what we can do is we can do things so that the rate of corrosion can be reduced. I do not know if we can make it 0, but we can make it slow, so that we reach the desired life of the structures. Now, when you look at steel, usually we think it is a homogeneous material, but if you look in microscope, this is how it looks. So, you have these different phases in the same steel, and you can see some lamellar structure here. So, that is all these actually leads to some kind of corrosion cell, local corrosion cell over there or in between here this. So, one of the phase might be corroding in preference to the other, and that is what metallurgists do, like to modify these things so that we can actually have better quality steel. Now, these are some one chemical composition for different type of steel. The main reason why I put this here is you can see the number of elements present in one particular steel. Yes, iron is very large in quantity, but there are other very small, like this one very small quantity, but so these are all very important in ensuring different properties of the steel. Now, what about concrete? Concrete is also very complex. I mean, you know that calcium silicate hydrase gives the it is a binding agent, or it gives the strength to the concrete, and we also have a lot of hydroxides in the concrete which give the high pH. Now, where is the pH? It will be somewhere 12 plus. This is the region where we are going to talk about when you talk about the pH of the concrete pore solution. Now, this high pH really helps us in ensuring that we can actually use steel and concrete together. So, this is the Pourbaix diagram, where you can see that if you talk about the steel, this is about 100 to minus 400. So, this is typical region where, or when you take measurement of, or the potential measurement of steel embedded in concrete, you will see mostly you will see something in this range. And point here to be noted is, if I have if I put a steel in a material with 12 to 14 or more than 12 pH, then I can actually have a region where there is a passive region is possible. That's what. So, this region I can really have a passive region. So, this is the reason why we are able to use steel in concrete and keep it there for a long time without any corrosion. So, what happens is, you put the steel in concrete. This is the photograph showing steel embedded in concrete, and I have drawn here a small green patch, which indicates that some passive film or a protective layer gets formed or on the it gets formed on the steel surface the moment you immerse the steel into the concrete. Now, you cannot see it. In the case of steel, we cannot see, it is very dense, colorless, dense, but it protects the steel below that from corrosion. Now, if steel has to corrode, something has to break this passive film, then steel will start corroding. So, what leads to this breaking of this passive film? Chlorides, carbon dioxide. So, you can see here, this is a bridge passing through ocean or marine environment. Chlorides can create problem for the passive film to break. Carbon dioxide can also lead to breaking of passive film, and of course, moisture and oxygen, they are the essentials. So, these two are the essential thing for corrosion to happen. If I can prevent moisture and oxygen and also keep it very low temperature, then I cannot have, corrosion can be stopped, but which is practically impossible to achieve that in many parts of the world. There may be, if you go to North Pole, you can probably get rid of high temperature, but most of the place where we live, we have moderate temperature conditions, and also you have moisture conditions. Now, so this is a picture showing in one of the metro cities in India. You can see a lot of vehicles here, they all are actually exhausting CO2, and you have this concrete structure right above this. This is just an elevated corridor. You can see, so all these concrete will have high, are actually getting exposed to high CO2. Locally you will have high CO2. Maybe CO2 will diffuse into the atmosphere, but local condition, if you look at, those concretes are actually getting exposed to high level of CO2, and also you have high temperature. You can see the sun out there. Now, when you look at the corrosion as a mechanism, there are 4 components or essential parts of any corrosion cell. So, there anode, you should have an anode, you have to have a cathode, and you have to have a ionic conductor and an electronic conductor. So, here you can see here the region which is corroding from the metal surface, this was the original metal surface. So, this much metal has been lost. So, this region is what is getting corroded, and that we call anode, and the remaining region on the steel. So, here it is the metal, the grey part is the metal, the remaining region helps this anode to corrode, and the electronic charge actually get passed from the cathode to the anode right through the metal itself. And if you are talking about an electrolyte like a water or even concrete, if you want to say, but water is also electrolyte. So, if you have it, then there is a ionic conduction happening through the water or through the interface between the steel, the metal and the electrolyte. So, you have this exchange happening here. So, that is ionic conductor. So, you have to have these 4 components. If I can get rid of one of this, I can stop corrosion, but that is not what that does not happen. So, what happens in the when you talk about steel in concrete, again similar thing, like you have on the anodic side you have iron which get this into Fe2 plus and 2 electrons. So, you can here you have this release of Fe2 plus into the solution, and provided you have enough moisture and oxygen, in that environment, what will happen is these two electrons which are coming from anode to cathode, and they will combine at the cathodic site. So, they will combine here, and then you will have two hydroxide ions formed. Now, why I put this picture here is, here you can see that this concrete pier is coming out of the water body, and here you can see a lot of corrosion or damage, whereas here there is no damage, and here if you go deeper into this pile, there also you will not see any damage, but here you will see lot of damage, or you are seeing lot of damage. This is mainly because when you go here, you do not have enough oxygen. When you go above the water body, you do not have enough moisture, but here you have both oxygen and moisture available in sufficient quantity, and also this wetting and drying accelerate the movement of chloride towards to inside the concrete pier. So, in combination we have more corrosion at the place where it comes out of the concrete. Now, this is a same equation which I showed earlier, just showing it in a more easy to understand manner. Here you can see at the anode you have corrosion happening. So, this Fe2 plus ions are getting into the solution, and then this negative charge is moving from the anode, electrons are moving from the anode to here, and now what is happening is this anode, these electrons are being absorbed at the cathodic site where there is enough oxygen and moisture, and it forms OH or hydroxide ions, which kind of move and react with this Fe2 plus. So, these two react and forming FeOH2. So, this reaction, like even though in this picture it is a very large in scale, actually this can happen right in the scale of millimeter or even a smaller scale, but for demonstration purpose we are showing it like this. Now, anode and cathode can coexist in the same piece of metal, because you even if you put one rebar or one steel piece into water or concrete, it can actually corrode. So, that means both anode and cathode are actually or can happen exist on the same steel. What is the reason for this? One reason is there could be a potential difference between 2 points on the same metal. So, when there is a potential difference between 2 points on the same metal, there will be a flow of electron from one point to the other to balance it. Now, what is leading to this difference in potential difference or potential is non-uniformity of the metal, non-uniformity of the electrolyte, and variations in physical conditions. So, I will show you these three cases in the coming slide. What does this mean? Non-uniformity of the metal, the first one, which is here I am saying the why there is a non-uniformity, mainly because of the difference in the microstructure and different phases available within the microstructure of the steel. You can see here, this is a simplistic explanation of this. What you see here, you can see this ferrite phase here and cementite phase here, and there is a possibility of electrons moving from ferrite phase to cementite phase. Now, here you can see that this portion actually loses ion Fe2 plus. So, this is functioning like an anode and this is functioning like a cathode. So, this can happen in any steel which you pick at the microstructure level. Now, next reason for the difference in potential was non-uniformity of the surface properties of the steel, or the this is another example where mill scale you can see here. Nowadays most of the steel, they clean the mill scale, but still there will be some remnants present on the steel surface. So, this is a picture taken from a metallographic study. You can see here this is the mold and mill scale and steel. So, what you see here is from when you take the steel, your steel surface is something like this. Okay. There are some there are some regions where mill scales are present and other region where there is no mill scale. Now, this will create a cell here, right here you can actually have a corrosion cell, you can have crevice corrosion happening here, like corrosion will actually start here and then go inside. So, these kind of mechanisms can happen which leads to again corrosion. Now, second point was non-uniformity of the electrolyte. So, if you like imagine you have some region where which is more acidic and some region which is less acidic or more alkaline. So, if you have a difference in this alkalinity, the region with lower alkalinity will actually start corroding or it will function like an anode. And for example, if you have chlorides, it is not essential that everywhere it will be the amount of chloride present in the concrete system will not be uniform. So, you may also see that some region has more chloride than the other region. For example, let us say in this case, if chlorides are coming from here, maybe there is an aggregate here. So, chlorides cannot go. So, they will try to move it this way and then reach this point. So, this point gets more chlorides than the one which is next to an aggregate. So, this is also causing a differential condition. Other thing is, if you nowadays you also have a lot of chemical admixtures which you put, one of them is corrosion inhibitor. Again, depending on the non-uniformity in the mixing, you may have some region with more inhibitors than the other region. So, this region will at some point in time this region will start corroding before this region starts corroding. So, again all these are showing that it is possible to have differential environment even though the steel is embedded in the same concrete. So, so the concrete properties are also varying from point to point. So, that leads to this differential. Now, other thing is about the physical condition. So, you know that concrete is a heterogeneous material, steel is also heterogeneous, and then steel we have ribs on the steel which causes some change in the physical conditions, the shape itself. So, for example, this is a detailed drawing showing like what can happen in at different points on the steel surface. So, for example, here you can see like if there is a rib here, there is a rib here, and then you can have the moisture trapped there, you can have an air void. In this air void you can see that where the moisture is there is no corrosion, but then where is the air there is more. So, the lot of these physical conditions can also lead to lot of variations in the steel concrete interface. Now, for example, this is a picture from our own lab where we can see that the top picture shows the steel. So, we after casting the specimen we exposed it for some chlorides, and then once the corrosion started we opened the specimen, and then what you can see is like there is a exact match of this thing. So, you can see this is a rust spot, this is a rust spot, all these region within the red circles they are rust, and when you see the imprint of that you can see there was actually a void, there is a void here, and everywhere it is very well matching with. So, it is very clearly we can see that these air voids, very small air voids which may be in millimeter scale, they actually lead to the initiation of corrosion which is matching with this what you see here. Okay. Now, what happens when corrosion starts, why our concrete structures are cracking, this is also a big concern. Now, when corrosion happens, it is actually there is a significant volumetric expansion, that is about 6 to 8 times increase in the volume. Okay. Now, here you can see this is the uncorroded iron or steel, for example we can consider to be steel uncorroded. When it expands it is getting from 1 to 6 times increase. So, this is all happening within the concrete, and there is a limit to which concrete can resist this expansive stresses. So, once there is a more expansive once the stress applied is more than the tensile strength of the concrete, it will tend to crack. So, you can see that crack radiating outward from the steel, this will happen. Now, if you have a cover concrete, this crack may happen only on one side, where if this is the cover concrete it will happen only on this, it may not crack inside because you have much more concrete inside. So, the cover region will start cracking faster. Now, to just show you how significant or how large this expansive stresses could be, this is a picture from Colosseum in Croatia. You can see this, this is actually rock. Okay. So, there was actually a metal piece inside this rock and it expanded and cracked the rock. So, if it can crack the rock, it can easily crack the concrete, which is man made rock. So, rock will have much so then I mean just to show you how significant that force can be. Okay. Now, this is again concrete in our own campus, one of the building you can see, and this is pretty much you might have seen this kind of corrosion happening in many places. You can very clearly see there is a bulging happening here, there is a slight bulging happening there. So, this steel rebar inside the concrete is corroding and expanding up to about 6 to 8 times, and which pushes the concrete cover outward and leading to cracking and then spalling. So, first it cracks, then it delaminates and then it spalls. So, here there is again another apartment building where you can see that actually this is not necessarily because of corrosion. I do not know the reason for this, but based on the experience what we have seen is in this particular locality there are actually buildings where when they were constructing they used sea sand or beach sand and chloride rich water. So, in addition when you have this clothes drying, they actually drop water onto these beams, and you can very clearly see that there is a lot of corrosion happening. And this also one why I put this picture is one more thing to emphasize that we should go for preventive maintenance. Why are we waiting until this happens? We should not let this happen. When we know that there is a possibility of corrosion, we should try to stop it right then and there by adopting a very good repair practice. And not just patch repair, means it is not that you just take it and remove it and then fill it with new concrete, it is not going to work that way. You have to really have a good patch repair. I mean it should be done in a durable manner. So, we will show you how we can do this repair in a durable, like so to ensure that it will actually last long. Now, in summary, what we covered today is cost of corrosion. The main or the key number which I would like you to remember is it is about 3 to 4% of GDP today, which we really have to work hard to reduce that number, and that essentially says why we need a corrosion management strategy. Main reason is we have large number of structures which we are building today. If we do not ensure good quality on those structures, they will start facing premature corrosion, and then we will have to spend a lot of money on repair. And then we also looked at some fundamentals of corrosion mechanism, and we looked at Pourbaix diagram. We found that at around 12 plus pH steel can actually prevent itself from corrosion, and that is the reason why we are able to put steel in concrete, because we have very high pH in our uncontaminated concrete. And then some reasons why steel corrodes, even though same metal, 2 points on the steel, one will act as an anode while the other one will act as a cathode. What is the reason for that to happen? And steel essentially is not homogeneous, it is a heterogeneous material, concrete is also a heterogeneous material. So, because of those reasons we have this corrosion happening on the anode and cathode can coexist or exist on the same metal. One thing I would like to say, this is my PhD guide, Professor David Trejo. This is a sentence from one of his slides. So, he tries hard to influence the next generation civil engineers to design not only for strength, but also for durability with minimum maintenance. It is very important for us to consider this today, because most civil engineers, when we talk about concrete, one of the important parameter which comes to their mind is strength, or to be precise 28-day compressive strength. That is not going to give you durability for the structure. So, you have to really think about how we can ensure durability and ensure durability not by spending a lot of money later on, but with minimal maintenance. Thank you. So, we will see next lecture on chloride induced corrosion and carbonation induced corrosion.